Present, please.
Good
Share
afternoon,
screen.
everyone. Yes, I do share my screen. Are you able to see my screen?
Yeah, we can see.
Yeah,
Yeah, please go ahead.
Yes. Good afternoon, everyone. I'm Dr. Natarajan. Today, I'm going to talk about the topic called "Was there a entity before the Big Bang?" In this talk, this is the plan for my presentation. So I start with the present day universe and Big Bang. Later, I move into the Big Bang theory, and we are going to see the Big Bang singularity. After that, we will going to see the quantum gravity and the singularity resolution from loop quantum gravity, and how we are going to approach the Big Bang in an alternative terms referred to as the Big Bounce. Regarding this talk, we have certain technical terms to understand what we are going to talk about. Initially, we are going to discuss about the Planck length. This is the smallest possible length in physics. Beyond that, you cannot do any physical calculations because the entire equations will start to diverge beyond this Planck length, and this is the at this Planck length, universe approaches the maximum energy. Then next one we are going to talk about is the space-time. The space-time is referred to as the background space in which we are hanging in and around. We means our Earth, the Sun, the planets, galaxies, all of the things are hanging in and around this space-time. Then next one is we are going to discuss is the quantum gravity is another technical term. We used to discuss about hear about the terms such as gravity, which is referred to from Newtonian gravity. From this aspect, we have changed the perspective as the quantum gravity. So we just fuse the quantum mechanics with the gravitational principle, and another one is general relativity. This is referred to as the Einsteinian theory of gravity. He modified the view of gravity in his alternative perspective that the space-time is manipulating the objects in and around. As a result, the gravity exists. So these are very general technical terms which we are going to use it in often in this particular talk. So we start our talk. This is a snapshot from James Webb Space Telescope. This snapshot is from our night sky. This image consists of various galaxies, various planets, various stars, and lots of other information. You can see, if you zoom into it, you can see the gravitational lensing effects, as well as the effect of dark matter. This a small pixel in the entire night sky. So from this we can start our journey. How big the universe is, how it could have been started, how it could have it going to end. These are all the questions we can ask on this picture. Based on this picture, we are going to discuss about few things about its past and present scenario. The present day universe have emerged from the Big Bang. It has the billions of years of evolution. So the cosmological model, which is consists of various theories, it says that universe is expanding as well as it is cooling, and it is its contents. We're going to see the contents of the universe are becoming less dense and more diverse. The present-day universe consists of various types of matter as well as energy, such as ordinary matter, dark energy, radiation, and gravitational waves. These are all the known constituents so far. The present-day universe consists various structural phenomena, such as galaxies. In our night sky, we used to see the stars, as well as if you see it in a powerful telescope, you can see some galaxies, you can see some supernovae, and recently we have discovered the images of first images of the black holes, and some radio telescope informations give you the cosmic micro background, and later you can see the gravitational lensing. The present-day universe is estimated to be about 13.8 billion years old, as well as it is about 93 billion light years across. This is the current scenario of the universe, and these are all the contents of the universe. Our universe consists of 5% of normal matter, 26% of dark matter. The dark matter means the matter cannot be interacted with the ordinary waves, which means we have four types of forces: gravitational force, electromagnetic force, weak and strong nuclear force. These are all the known way of interactions. But dark matter doesn't interact with any of these manners, so that is why we put it in a dark sector. So that is dark matter, and another one is dark energy. So universe is expanding. The expansion is moving away against uh, the pulling of the gravitation. So that is why we say it as dark energy. It's just moving against the uh, gravitation. So we can ask few questions: how the universe might have begun, what are the starting point of the universe, and to answer this question, you need to think about how the universe might have been um, uh, emerged. So just we are going to run the evolution as backwards in time. So that ends into a point where the space and time ends in a particular single point from which you cannot you cannot have the any kind of evolution in that particular point. So that is what we name it as a Big Bang singularity. So we are going to discuss about the theory. So Big Bang is a scientific theory that explains how the universe began from the initial high densitized and highly temperature and highly curved initial state, because so uh, consider imagine this one. So universe is expanding, right? So the stars you see in the night sky is usually moving away from us, the earth, as well as the solar system, even as well as the Milky Way galaxy. So suppose if you move in backwards in time, so in a particular time, these entire universe supposed to be in a particular smaller value. So that is what we call it as the Big Bang singularity. According to this theory, universe started from a single point called as Big Bang singularity. Then it stretched and grew its current size and the shape. In fact, we don't know about the shape of the universe. That is in the scientific perspective. Then we know that the universe is expanded. So then the theory, Big Bang theory, is supported by various observations such as expansion of the universe, cosmic micro background, and abundance of light elements. So the uh, this is the possible explanation. This image is a possible explanation for the Big Bang. So now we are in an around 15,000, 15 billion years after the Big Bang, around. So then, if you run backwards in time, we end up with a singular point where the entire substance of the universe might have plunged into a point called as Big Bang singularity, where universe might have in a huge temperature, as well as the entire force of the nature are combined into a unified force. So there are some issues on the Big Bang theory too. We cannot explain how the singularity might have originated. Then how what is beyond this Big Bang singularity? These are all the question still remains for the classical physics. The Big Bang singularity compatible for the standard model of cosmology. In fact, standard model accepts the universe is expanding, the universe is cooling, and we have the standard model of particles. The entire thing can be pinged into the model named as Big Bang theory. So, as I said earlier, there are some issues in the Big Bang. So we don't know what is before that particular starting point. So simply understand one thing: the singularity. So the technical term singularity is the starting point for that universe. You cannot ask what is beyond that starting point, or else what else created that particular starting point, because we don't know the answer. Then we don't know the answer for the substances like dark matter, dark energy, and formation of the galaxies. Still, there are lots of scientists are working on these issues. So you can ask the evidences for the Big Bang. So as I said, the Big Bang is the most known model for the universe. So for the case of evidences, uh, the first thing, the universe is expanding. So we know that uh, uh, the stars and galaxies are moving away, and then abundance of light elements. We have measured the amount of hydrogen, helium, lithium, and its presence in the universe. These elements might have originated from the initial stages of the universe. That is another supporting point for the Big Bang. And cosmic micro background radiation. In fact, our background space-time consists of small temperature around 2.7 Kelvin. This is the very smallest temperature, might have originated from the some hot past stages of the universe that might have been the Big Bang. So that is another evidence for the Big Bang. And uh, there are lots of theories and models supporting the evidences for the Big Bang. So we ask the initial thing, the Big Bang singularity. Big Bang singularity is not a place. It is a hypothetical mathematical point. You cannot access it in a physical form. So it is a mathematical point from where the time and the space might have originated. Then from that point, universe has begun and evolved. So our known theories, such as theory of relativity or else any kind of evolution, cannot explain the Big Bang singularity because it is too smaller in nature and too higher energies, as well as high um, highest nature of its curvature. So these are all the issues from where we cannot explain the Big Bang singularity, as well as you cannot explain what is beyond this Big Bang singularity. In any consider in any case, for example, consider the evolution of the universe. you can ask what is before the humans. Might have the apes, might have the chimpanzees. So this evolution ends up to the single cell um, organisms. So, but you cannot ask uh, how the biological mechanisms emerged in this universe. But that is related to the evolution of the universe. That is related to the how these elements might have come to the earth. And end of the day, you run back to the question. You can the every question might end up with the Big Bang singularity. So far, what we have known this know about this Big Bang singularity. As I said earlier, our known theories failed at the Big Bang singularity due to its high density, high temperature, and highest temperature, as well as the curvature. Then we need to we need to develop certain special kind of theories to explain the nature of the singularity and nature of the Big Bang singularity. Then we need a theory called as the quantum theory of gravity, or as quantum gravity. That quantum gravity is to relate the quantum mechanics as well as the theoretical related. We are going to see it a bit later. Now, we can ask the question, what is before this Big Bang? So, at the initial stages, some big interactive massive particles might have formed. Then later, uh, neutrinos formed, combinations of atom. Then first stars might have created galaxies, and everything is started from that Big Bang. So still, you cannot reach before the Big Bang. So uh, the known theory of general relativity explains the gravity as the manipulation of space-time. But in the Big Bang, there is no space, there is no time, there is no such kind of known evolution. So that is why you cannot explain the case what's beyond the Big Bang. So so far, I'm talking about the singularity. So what the singularity refers to? We can see this picture. Our sun curving the space-time around its curvature, so around its horizon. Then the higher massive than the sun, we can call it as white dwarf. It's a kind of star that curves the space-time more and more, and further a neutron star, a densest formation of star that even bends the space-time even further. Then another thing is black hole. So even that distorts the space-time even further. So end of this space-time, you can point out a mathematical region called as the singularity. Then the necessity for quantum gravity. The necessity is to understand the singularity. So singularity is the is available in various places of the universe, in even at the core of the big core of the black hole, as well as the initial stages of the universe. The quantum gravity is had a plan to fuse the theory of general relativity and to the greatest theory of 21st century, referred 20th century, the quantum mechanics. So the quantum mechanics talks about the particles, fields, and forces of the nature, and whereas the theory of relativity explains about the nature of the gravity, which means nature of the space-time. We need to fuse both things together. Then you can understand the nature of the quantum nature of the space-time, as well as quantum nature of the Big Bang singularity. So to do so, various approaches are there, such as string theory, such as loop quantum gravity, such as causal dynamics, triangulation, non-commutative geometry, twistor theory. There are lots of approaches on the same problem, but still we don't have any consistent theory for the same problem. So every approaches have its merits and demerits, but you cannot have your whole theory which explains the mathematical view of the gravity as well as the quantum mechanics. Uh, you need to work out various aspects of the quantum mechanics, such as uncertainty theory, such as probability, and discrete nature of energy and matter. And these are all from the quantum mechanics, as well as from general relativity, determinism, and continuous fields of space and time. These things are has to be mapped together. So whereas earlier we have mapped the weak force into electromagnetic force, such a kind of mechanism also applied on the gravitational force as well as the quantum mechanics to do the quantum gravity. But still, we don't have the full theory of quantum gravity. A perfect quantum gravity theory should unify the all forces of the nature, such as strong, weak, gravity, as well as electromagnetic field, as a unified force, and has to explain the quantum nature of the space-time too. To solve these things, there is one method called as loop quantum gravity. Related to other methods, it has lots of consistencies. So that is the way we are working on the loop quantum gravity. So the loop quantum gravity based on the spin network formalism. There are two set of formalism are there. One is canonical um, method. Another one is covariant method, which works on spin networks. You people might have know about the spin. So with the help of spin, so you are working on the spins, quantum spin. With that idea, you can apply the same spin structure to the quantum nature of the space-time, and with that formalism, the gravity can be studied. It's called as loop quantum gravity. So the loop quantum gravity has the numerous successes and numerous applications. So it is able to explain the minimal length of the universe. As I said earlier, this is the Planck length. In the Planck length, there are the curvature is huge as well as the energy is huge, which means the initial stages of the universe can be explained with the Planck length. The loop quantum gravity explains the Planck length, whereas Planck length means the initial stages of the universe. Means the loop quantum gravity has the ability to explain the initial stages of the universe, or is the Big Bang singularity. And then the greatest uh, uh, resolution of the quantum mechanics is it explains the matter as well as the energy as the discrete entities. The loop quantum gravity also explains the space-time as the discrete entities, like chunks of space-time. Then it explains the Big Bang. The Big Bang was not supposed to the initial point, whereas it provides a huge alternative to the, or else huge resolution to the Big Bang as the big bounce. Big Bang, the big bounce explains that the Big Bang is not the actual starting point. Before the Big Bang, there might have been the another sort of universe that ends into the Big Bang. Then its energy density reaches the critical density. Then beyond that, universe starts to bounce off. So it's a kind of revolution. in the Big Bang as well as the cosmology. Uh, in the first time of our history, of our scientific history, we are able to explain as well as understand what the Big Bang means. So that is explained as the big bounce scenario. Now, here this picture explains the same. So we start from cosmic micro background. Then, as we move backward in time, we end up with the singularity. Beyond that, you cannot extend our known laws of physics. But loop quantum gravity says that these singular spacetime is the discrete kind of spacetime. Beyond that, the trajectories can be explained as a kind of pre-bounce. Like similarly, we can say that previous to the human is another ape, right? From the chimpanzees, we have come, right? Chimpanzees, the evolution of the chimpanzees end at the starting point of humans, right? Homo sapiens, right? It's a kind of, it's not the direct analogy of the loop quantum gravity. It's a kind of explanation. So from that big bounce, there you can see some a mirror image of two universes. From the big bounce, the one universe in forward direction of the time, it's moving forward in time, which is expanding. So on the other side of the image, other side of the mirror image, uh, a previous universe starts to end its evolution at the big bang. So it is kind of cyclic evolution of the universe. That is referred to the uh, 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 big bounce. So you cannot say there is a initial, there is a exact starting point of the universe. So we see the big bang is the starting point of our universe, our cycle of the universe. But there might have been previous cycles of the universe. So you can so we are going to see some mathematical analogy of the same. So here we in the loop quantum gravity, we introduce the Hamiltonian uh, constant. This is related to the Einstein field equations. So here it is the Hamiltonian H cap is a Hamiltonian operator. This involves holonomies and fluxes, as well as there is a special connection which is introduced here as Fabro-Stecker connection. So these connections work together and construct a theory of loop quantum gravity. Here, the same Hamiltonian constant is applied to the cosmological model, such as FRW model. So, from that model, we are able to explain how the Big Bang works. So, simply we can resolve the Big Bang singularity with that effective Hamiltonian constraints. From that aspect, we are able to understand the big bounce as a kind of um, a scenario, like consider an example. Suppose you have a sponge. So in that sponge, you pour some sort of water. The sponge can hold the water up to 500 ml. So if you pour more water, more than 500 ml, the sponge cannot hold. So it starts to leak the additional water which you pour on that sponge. In same scenario, the here for this case, 500 ml is the critical value for that sponge. So beyond that, it starts to leak. So here it is near to the Planck density, namely 0.4 of Planck density is the critical density, beyond which it starts to leak. So that is called, referred to as the big bounce. So in the big bounce is the possible scenario for the origin and evolution of the universe that avoids the Big Bang scenario. As what we have seen earlier, you cannot avoid the Big Bang singularity, which means your theory starts to end. But here, the Big Bang singularity can be avoided. Even your theories can be expanded beyond this singular point. So also you can ask a question. So as I said earlier, there is no space, no time before the Big Bang singularity. So you can cross the scene. Then how you can define the time? So time is referred to as some scalar fields. So the evolution of scalar fields can be expanded even beyond the singularity. So big bounce is a smooth transition from contraction phase to expansion phase. So here, the imaginary example of the big bang. From the big bounce, there are sort of two sort of expansion. One is from the negative times of negative of the time, and another one is positive in the time. Big bounce is the starting point. Hence, Big Bang singularity can be avoided, and in this critical point, you can explain the evolution as the spin networks. Then the bounce is not a violent explosion; it's a smooth transition, like from like a quantum mechanical transition. It starts from one cycle to another cycle. This is a kind of spin network scenario. You can work it with vertices and as well as the edges. In the edges, you can have the spins. On the vertices, the space time is usually concentrated on, and uh, using these vertices as well as its angles, you can explain the evolution of the space-time at the quantum level. In fact, there is a additional application for this kind of formalism, spin network formalism. In recent days, the quantum computers are quantum computing people are trying to simulate the initial conditions of the universe with the help of this spin network formalism as within the quantum computers itself. So this is a different solution for the same problem. Then using this spin network formalism, you simply find the space-time as the discrete chunks of uh, space. Like simply, we are able to see the light, right? What you see, the light is it's like a continuous entity. Uh, in nature, light is not the continuous entity. It is chunks of photons, the massless particles named as photons. Simply, in a colloquial meaning, the photons are the atoms of the light. Not exactly, the atoms are the light. So you can say it like in similar fashion, you can say these spin networks are the atoms of the space-time. So you cannot do the directly you cannot do the experiments on this because it is in very smaller scale and higher energy scale. So that is why you cannot experiment directly in perspective, but you can simulate in laboratories. So as I said earlier, there are another approaches on the same problem, such as string theory. But string theory and the loop quantum gravity moving in a parallel perspective, both are working in the same problem, but they are having some differences as well as some similarities. They both have the minimal length scale. In this minimal length scale, they started to think like the stringy fashion, as well as we started to think as like spin network fashion. They both are trying to explain the thermodynamics of the black holes, and but the condition is the background independence. So once you start to explain the loop quantum gravity, you need to have the background independent theory, whereas string theory are working on the background independent formalism too, as well as the cosmological constant problem. I said earlier, the dark energy. The name of the dark energy is given as cosmological constant in some perspective. They are working on how the measured value of cosmological constant is having the greater differences with the theoretical understanding. And these are some open problems. The problem of dynamics. So you cannot you have to um, explain the dynamics of the space-time. The problem of observers, how we are going to construct and interpret the physical observables of the loop quantum gravity and semi-classical limit. So these quantum gravitational formalism is from the it is in the quantum gravitational regime. So you need to work it out on the semi-classical, how you can recover the things in semi-classical level, as well as the matter coupling, how these spin networks are going to interact with the fermions as well as the other uh, uh, bulk materials. So that is another problem. And phenomenology, how we are going to experiment it, and what are the possible signature and effects of the strings in the cosmology. These are all the open problems in loop quantum gravity. As a summary, it is the loop quantum gravity is a theory of quantum gravity that tries to explain the origin and evolution of the universe without invoking the singularity. So we simply remove the singularity. It proposes that universe is not the one-time event, but the cyclic process of the expansion, contraction, where each cycle is separated by the quantum bounds. The bounds is the smooth transition. As I said earlier, it is not an explosion. It's a smooth transition from contraction to expansion, where universe reaches the minimum size and maximum density, but does not become single. In fact, we remove the singularity. The scenario avoids the problems and puzzles of the Big Bang theory, such as initial and boundary conditions, and the entropy of fine-tuning and the origin of matter and radiation. It provides the natural explanation for the observed homogeneity, isotropy of the universe, as well as the quantum fluctuation and the seed for the cosmic structures.
Okay, thank you, Dr. Natarajan. Now the
Thank you,
talk
sir.
is open for discussion. Any questions? Maybe I'll start with a simple question. Maybe
Yes, sir.
Tracy also. Recently, there was a news that the age of the universe is not 13.8 billion, but is 28 billion years. What is the reason, or what is the buzz about?
Yes, sir. But we are seeing we are calculating the age of the universe from the FRW universe, and so far the known laws as well as known experiments supports this claim, supports this evidence, and there was a paper that says that the age of the universe is supposed to be double, and there are such a calculations which relates the Hubble value to the Hubble time. But from that various initial conditions, you can obtain these sort of answers. But evidently, this not supposed to be the answer. Later, various cosmologists refuses that this is not the age of the universe. This is some theoretical misinterpretation of the known values of the theory.
Questions?
I have a question. Thanks for the thought-provoking talk, Dr. Natarajan. I just want to know
Yes, sir.
about your thoughts on multiverse, and if just in
Yes,
case
sir.
if multiverse exists, if there are like many multiverse, is it possible that universe is a child of this multiverse? Is it multiverse expanding or something? Just wanted to know your thoughts on that. Thanks.
Theoretically, it is possible, Anna. There are lots of models from string theory, as well as Swampland conjectures, as well as landscape. Those theories says that our universe is not the single entity. We see a continuous evolution of the universe, continuous cycles of the universe as the single entity. But there might have be the various possibilities for the multiverse. There are some parallel universes, but the thing is, we cannot reach there. They are causally disconnected from each other, and the multiverse is possible because you can see from the quantum mechanics as as a spectrum of cosmological constant. There are lots of universes are possible as a spectrum of vacuum as well as cosmological constant, but we don't know the laws of physics are same in those universes, because we have the minimalistic amount of cosmological constant here, as well as the gravity is balanced here. In some cases, the cosmological constant might have been greater, which means the dark energy might have been greater levels. So that is why those universe might have been expanded in greater extenses. Uh, the universe, the universe which we are living have the ensemble of uh, uh, ensemble for the possible civilization. So that is why we are questioning about the universe. But there are possible universes. There might have been the advanced civilizations, but it is possible. And also, our universe, like of another universe. Yes, it is possible. The theory referred to as pocket universe principles. We are kind of a pocket universe. Like there are another pockets might have been there around the universe, but there is no evidence or no observational evidences are possible for this claim.
Any
Very
other
interesting.
questions?
Thank you. Thank you.
So I have a question.
Yeah, please go ahead.
So this question may be very, very novice question. Actually, I want to know: does the space also shrink when the singularity happens? Does the
Can you repeat it,
space
please?
does the
Yes.
space also shrinks when the singularity, at the time of singularity? I mean, at the Big Bang, at the instant of Big Bang, the space also shrink, or space is not affected?
Yeah, even the entire universe, the space and time might have begun from the Big Bang itself. During the Big Bang, at the initial time, there is no space, there is no time, everything. So we see the space in and around us. Once was in the Big Bang singularity. So every thing in the universe uh, uh, once inside the Big Bang singularity. Even the space itself, there is no space outside the Big Bang.
So all the matters at the time of Big Bang transfers to energy, or what does it transfer to?
No, the entire energy as well as the matter. So they are not in the same form. We are seeing the matter as a kind of composition of atoms. But in the Big Bang singularity, there was no such distinguished things. Even the bosons and fermions, the matter particles, as well as the mediator particles, supposed to be in a same state, that is the GUT state. So you cannot say it is in terms of normal matter. So we see it in a kind of atoms. So you cannot see it in a normal matter. So simply say it as the energy. Right.
So is it nothing or is it some energy? I mean,
In some formalism, kind of no boundary proposal from Stephen Hawking, the Big Bang singularity is nothing. It is emerged out of nothing. There's supposed to be no initial stage, as well as some professors like Alan Blankin are proposing the same. There was nothing. It's vacuum of space time, vacuum of matter, vacuum of energy. There is uh, no known theories cannot explain the initial such an initial state. So you can simply say it as the vacuum, but that vacuum are able to um, um, uh, emerge such a Big Bang singularity. But the same thing cannot be recreated in any sort of energy scales in the present universe.
so my last question is, so the James Webb Telescope we recently launched. So this explains a lot of old things.
Yes.
So does it support this Big Bang theory?
Yes.
How does it support it?
The James Webb Space Telescope is able to find the formation of the initial stars. Since whatever may be the powerful telescope we are able to construct, we can only see just to the 3 lakh years from the Big Bang. From the beginning to 3 lakh years, there was no photons emitted out. So the universe is not transparent. Universe is supposed to be opaque. So the first photons emerged is after the 3 lakh years of the beginning of the Big Bang. So the James Webb Space Telescope is able to find out the very initial stages of such a scenario. It is predicted that the initial conditions, such as how the star, what are the possible scenario for the star, then obviously it will support the Big Bang, and we can find out a time chart of the evolution of the universe from Big Bang evolution of the universe from the James Webb Space Telescope data.
So is it possible that the figure you showed, that like balloon kind of shape, the universe expansion like balloon? So the diameter of the universe was smaller in the previous time. So James Webb Telescope could it show that the diameter was less in previous time, many billions years ago, like this?
No, it is not possible. In fact, our analogy says like balloon kind of expansion, but the we cannot predict its structure. So if it is a kind of balloon kind of structure, there is something outside of it. But you cannot say outside of this expanding universe, initial stages of the universe. And James Webb Space Telescope could not explain could not predict, as well as could not find out these kind of balloon analogical expansion. The expansion is there. It is able to find out the expansion of the stars, initial stars, expansion of the galaxies, but not like the expansion of the balloon of universe.
Thank you.
Thank you.
Any other questions? Okay. If not, let's thank Dr. Natarajan. Thank you. Thank you, Natarajan.
Thank you.
So let's move on to the next session. I'll pass the mic to Ramu. Dr. Ramu, please go ahead.
Yeah, good evening, everyone. So we came to an end of this today's symposium on magnetism. So it's my honor and pleasure to give the closing remarks to the 13th IEEE Magnetic Symposium. So I have to take this opportunity to thank each and everyone who has contributed for the success of this symposium. Firstly, I would like to thank IEEE Magnetic Society Singapore chapter, especially Prof. Prem, for giving me an opportunity to chair this symposium, and SPMS NTU for hosting the symposium. I would also like to thank co-chair of the symposium, Dr. Durgesh Kumar, for his continued support for organizing the things. So I would also like to mention special thanks to Prof. Manuel and Prof. Tanaka for the plenary talks, which is under IEEE Distinguished Lectures, and other keynote speakers who actually accepted the invitation for giving the keynote talks, and also like public lecture speakers for their interesting talks. So these talks were actually different from different parts of the globe and covered a wide range of topics in the field of magnetism, as well as some special talks including synchrotron and before Big Bang. Apart from these talks, we also had a student presentation competition to encourage local PhD students to present their work. So for this case, like I would like to mention thanks to Prof. Rensha and Prof. Pinaki for being the judges of the student competition. So the factors that were taken into account for considering the winners of this competition are novelty of the work that presented, clarity of the slides, quality of the presentation presented, and answering the questions. So there are three participants, presented their works. So basically, there are three prizes. So it is the competition for to be the first one. So I will announce the the winners of this presentation. Apart from this, there were some international students also presented their works, so they will get the presentation certificate like to be part of this symposium. So apart from this, there are also IEEE membership vouchers that will be distributed to the presentations, student presentations. They can actually use that to take the registration for the IEEE. So now it is time to announce the winners of the competitions. So I will start from the bronze because there are three prizes. One is gold, silver, bronze. I will start from bronze. So the bronze winner is Hasibur Rahman. He presented on magnetic domain wall-based synapses modulated by DMA. I congratulate Hasibur Rahman for the bronze winner. So the next two presentations, winners, I will pass it the stage to Durgesh Kumar. He will present the next winners of the presentation.
Yeah. Hello everyone. So that wasn't really necessary, but he wanted me to participate. After bronze, the silver medal goes to Basa for his paper on a layer neuron via synthetic antiferromagnetic coupling. So congratulations to Basa. And the gold medal goes to Saurabh Munna for his paper on bias field free spin Hall nano oscillator as spiking neuron. So congratulations, Saurabh. Thank you all.
Pass this to Prof. Prem. Prof. Prem, you want to say something?
Yeah, so I want to give my appreciation to Dr. Ramu and Dr. Durgesh, who took the load and organized the symposium successfully. So I hope we'll continue this tradition of the magnetic symposium every year. And I request participation from all of you. And last but not least, I also want to thank all the students from other countries. I mean, there are people like some other students from India and Japan who also participated in the symposium. So by thanking you all, let's close this symposium. Thank you. Bye-bye.